intimidated or not. So be prepared for that. And I will start that most likely on Friday. So I'm planning to thoroughly question you on it. So it'll take a little bit of time for each person. So to get everybody through, I'll start the oral portion of your final on Friday. At first I'll take willing volunteers, but if there's no willing volunteers, then I'll start pulling people. So make sure you're ready for that. We'll do...
Wait, your exams on Monday?
The written exams on Monday. Yeah. Talk to me after class. Awesome. We'll see. Yeah. Okay. And all that, of course, is up to change the schedule. As you all have been very flexible throughout this class, which I appreciate. So, any questions on that? Okay. So, APUs, or Airborne Auxiliary Power Units, it is chapter 49 of the ATA. In your textbook, it is all scattered throughout, because there's a little bit about APU fuel and fuel suction. There's some about APU starting and starting. So this brings all that nice and concise together in one PowerPoint. If there's anything that you want to study deeper, whatever section it's talking about, whether starting or fuel, go to that subject section of the textbook. But in the Jeppesen textbook, which you've been referring to for some of your labs, there is, in the turbine engine section, a nice little section just on APUs. So that's a good resource if you want a nice summary of an APU. So diving in, what demands do we have for ground power? We need it for engine starting. Do you remember from last week what is the most common type of starting system on large engines?
Air starter.
Good, air turbine starter. So you need air for that. Air conditioning on the ground. Hot summer day, passengers load up early. You want to keep them nice and cool. Lighting for the cabin, cockpit. Entertainment. Show your passengers movies. And food preparation to get all those things started and working. Electrical ground power is not available at some airports. So the solution is to have an aircraft auxiliary power unit. And some airports do have ground power units that are actual APU engines, so you can have the same engine on your ground power. So APU, when we're talking about APU, that does mean auxiliary power unit, and that supplies the alternate source of here, the next slide is shows a little bit more, but here we have our air coming in, and I think I'll wait for the next one to show you some of the interior guts of it. But it's a pneumatic and shaft powered gas turbine. Its engine is controlled and protected by 3 systems. So the fuel system, it's a turbine, so we need fuel. That fuel is also controlled. A lubrication system, yes, we do need the proper oil, and then an electrical system. And it can be split into 2 sections, the power section and the gearbox. So here we have our power section where our turbine engine is running, and then our load compressor, which is compressing all our air that is going to be operating the systems on the aircraft, and then our gearbox with accessories like our fuel control unit and all those things. Here is a cutaway view of it. So the APU operates by the compression of ambient air by a single entry radial outward flow centrifugal compressor. So centrifugal compressor, and that throws the air outwards to, what are these units here? Very good. Down onto our what? Very good. And out the exhaust. But then the turbines are driving what? And the load compressor. So here, we're sending all our air, because we need a lot of air going out to everything we're trying to run off of this. And the rotating shaft power of the turbine rotor drives the compressors, the accessories, and the gearbox. The gearbox section supplies a 12,000 RPM clockwise rotating mounting pad for the generator unit. Any questions on that?
A question for the load compressor. Is that load compressor typically lower compression than the actual compressor for the burning section?
Good question.
Otherwise, that's a good question. When you figure it out, let me know. No, I'm not sure. That is a really good question. The engine compressor is going to compress by heat or combustion. But as far as the load compressor, typically it's probably got a higher pressure than the aircraft would be. Just about every aircraft uses an average of about 45 psi. So if you put out 50 psi, it's going to be a low limiter to make sure that the air is available, but it's only going to be 45 psi in the whole system.
So the air inlet, we talked about the plenum, which is directing that air, making sure it gets in at the correct direction. Our air inlet can be found on top of the fuselage or on the side of the tail cone. Next slide will have pictures of those differences. Some aircraft have an APU inlet door that can open and close, while others just have inlet ducting with a stainless steel screen. Be very, very careful. Around And this is the door that would open up. So that door, if it's not the whole way open, the APU, the start sequence is going to be disabled because you need that the whole way open. So if you're having trouble starting an APU, check that door, make sure it's open. Also, when you're working around the aircraft, be super careful to protect this. If you drop something inside, it's going to go right into the compressor. And now you have to take out the entire APU. Not a good day. So be very careful. So do not spray or drop anything inside. And there are ports for the inlet ports the air down here into the air inlet plenum. So that is got to direct that air to the plenum. So already looked at screen versus the door, different styles that you'll see. APU operation. The APU is a self-contained power source and requires only a source of fuel and electrical power for operation. So the starting, acceleration, and operation of the APU are controlled through an integral system of automatic and coordinated, so together, pneumatic systems, electromechanical controls, and by the APU electronic control unit, or the ECU.
Is there any sort of regulation or anything that requires you to do the size or anything?
No. But it would be more on starting needs and accessory needs. Yeah.
Or the aircraft needs? There's no regulation that.
So, to recap this, to start it, bring it, accelerate it, and operation, we have a little bit later is a push switch or button, and then electrical, mechanical, pneumatic, the electronic control unit are all working together to make everything happen at the correct time to make it operate as it should. So one of those is the engine fuel and control. So the function of the APU fuel system is it has to supply the correct quantity of fuel flow, keep the correct pressure necessary for smooth engine acceleration, and keep a constant 100% RPM at the idle and at different load conditions, and then supply filtered fuel from fuel tanks to the fuel system. So APUs are running at rated speed no matter what the load on them is. So they're running 100% whether they have nothing loading them down, or if you've got trying to start an engine or have air conditioning running. So it has to give more fuel if it's calling for more load, or back off the fuel if it's not pulling a load. So all that has to be sent. Has a fuel control unit that includes a metered fuel bypassing technology, which improves fuel metering accuracy at low flow range that is necessary for high altitude starting and operation of APU. So all the thought that goes into this design and what it's required to do, it has to be able to start well and clean at sea level, but also if you get up to altitude and for some reason you have to be able to start an engine, it has to be able to do that as well. All that factored in. Within the FCU is a torque motor metering valve and a differential pressure regulator. The ECU, or the electronic control unit, sends signals which put the this is something I noticed about this diagram, and might be unique to APUs. So we have fuel nozzles, the fuel manifold, and here it says, well, this here is a flow divider valve, and here off this side we have secondary fuel manifold, and off of this side, primary fuel manifold. Fuel control unit sitting back here on our gearbox, filter down here, and the solenoid valve up in here. This is kind of where those components are on the engine. Any questions on the fuel? Ignition and starting. The APU has its own ignition unit and igniter plug that operates off 28-volt DC power. Has its own electric starter motor attached to the APU that has an input voltage of 28-volt DC. The drive shaft of the starter motor has splines which engage a sprite clutch, like we're talking to some of the starters for the engines, until it gets up to operating RPM. Pneumatic power. The APU supplies pneumatic power in the form of the compressed air. The pneumatic air is for the operation of the aircraft's main engine starters and the air conditioning system. The air is monitored by the electronic control unit and controlled by a load control valve. So our ECU is saying, what's going on? Talks to the valve like, oh, more air, less air. The LCV, load control valve, is coupled to the compressor outlet. I have a diagram of all this in a minute. LCV is coupled to the compressor outlet, and the ECU adjusts the butterfly plate inside of it based on the quantity of bleed air needed and the APU exhaust gas temperature. So green is sensing what's going on, talking to valves to say, oh, you open, nope, you close, you open, you close. Pneumatic power and bleed air places the greatest load on the APU. So if you're asked in a testing situation, what places the greatest load on the APU, you will say pneumatic power and bleed air. So when we're taking that bleed air and all that pneumatic power off the compressor of the APU, you're taking its energy. But it's getting more fuel to keep it spinning. And there is a 1-minute delay on startup before APU is available. So you can't just start grabbing it right away. You have to give it a minute to spool up before you can use that. Here is a diagram of all those valves and everything that I was talking about. So, kind of perspective, here's gearbox, compressor air inlet, fuel coming in, flow divider, primary fuel nozzles coming over here to our secondary fuel nozzles. So we're taking that bleed air, and here is a test port up here. We'll start over here. Load control valve. So that is a valve across where our bleed air is coming out, so that can open as we need it or close off. And we're sensing also ambient to make a balance so it knows what's going on outside to compare it to the bleed air coming off our compressor. A surge valve for protection, also a sensing for ambient air with a solenoid valve. And coming up here, that torque motor, and we have a vent, so all these, most of these are sensing ambient or vent for overboard. And our control pressure regulator, which is also sensing coming in here, and that also has ambient sensing. Then coming over here, some of these components, so load control valve here, you can see it up here, and a surge control adapter, that was this guy here, and then here's our compressor air just coming off there. Yeah.
Okay, just so that there's no confusion, at the beginning of the presentation, they talked about an APU with a load compressor, a separate compressor. Not all APUs have that. This happens to be a breakdown of a typical APU for both the combustion air, well, I should say the combustion air is being used for both combustion and aircraft cleaner systems. Okay? So when you see something like this, the reason why it's got a little bit more monkey motion to it there is that until the APU gets up to 100%, we have to unload that compressor for running at lower as it's accelerating to 100%. So that surge valve will open and actually lead some of the air off into ambient. Actually, there's a little right arrow coming out that. Yeah, that's just going dumping out into ambient. So we're unloading the compressor and allowing the APU to get up to 100%. Once it gets up to 100%, that little valve will close, and now everything's cool. Then, if we want to tap off air from the compressor, we're going to open up that valve. The fuel controller is going to be immediately sense that the RPM wants to drop because we're bleeding air off the compressor. So the fuel controller will automatically start adding fuel to
you hit APU master on, and then start momentarily is held in to start the APU. And here, ooh, does this ring any bells? Pun intended. What is a lot of this panel for? Might not get us. First, thank you, Lyle. You got it. Are we gonna need bells or buzzers? Yeah, so a lot of this is your fire detection, and we had talked about fire systems class. But here, see, let me do that. You have off, run, and start switch here. And we're going to our electronic control unit with the starter motor, start contactor, and our bus. The sequence that the APU follows is before start, the ECU does a built-in test for condition and operation. Then the ECU energizes the fuel control unit and the APU feed shutoff valve on the aircraft. An indication in the cockpit is given that the APU invite or APU ready light illuminates. So you want one of those to come on. The ECU energizes then the ignition and starting system and the start APU contactor. Then the APU fuel solenoid valve opens. APU RPM becomes stable at 100%. So again, starting ignition, and it's giving fuel at the right RPM until it comes up to 100%. Then, just like our regular engines, the ECU removes electrical power from the ignition and starting system. So we're started, we're running, we're good, so then ignition and starter is taken away. On shutdown, the APU, the electronic control unit, ECU, simulates an overspeed condition when shutting down the APU. Before shutdown, a 3-minute cool down period is recommended, which requires the bleed valve closed so the EGT can stabilize. The cool down period minimizes thermal shock of the APU. Be aware, when shutting down, you can leave the aircraft on essential battery bus. Watch the APU exhaust gas temperature and RPM to decrease at least 5% RPM before shutting your batteries off to make sure you don't have a relight or any hang fire. So just like on a regular engine, because it is a turbine, you don't want anything to relight on your shutdown.
And you will find that last paragraph there,
Yes.
you'll typically find that in all the aircraft flight manuals. Because if you go up here and start the APU, you're going to follow the checklist on the
Right.
aircraft flight manual, and you always have those things that, like on shutdown, it'll say, make sure you're below 5% before shutdown. There's one more thing. Are you going to go into the overspeed at all?
No.
Okay, the second line says that, oh no, the first line says that when you shut the APU down, it simulates an overspeed. Well, the worst thing that can happen is where something happens to the APU where it overspeeds. So you're always at 100%. And let's say, for instance, you accidentally get de-icing fluid in the inlet while it's running. That de-icing fluid can burn. It'll augment everything in the air going into the combustion chamber, and also, you can overspeed. So the ECU senses anything when it hits 110%, it'll shut that ECU down. So that overspeed sensor in the ECU needs to be tested. What better way to test it on every shutdown? So when you hit the off button to kill the ECU, it actually does. It sends an overspeed, take overspeed signal to the ECU.
compressor inlet temperature across the bottom. The APU will not use pneumatic power above 20,000 feet, so there we go. Can still use a generator and have APU running up to 35,000 feet. But if you need to restart the APU, you need to descend below 35,000 feet for it to be able to operate.
Not all APUs are flight APUs. Just depends on how the aircraft manufacturer designs the aircraft, whether they want
meeting is coming Saturday, May 10th.
Everybody's home.
I haven't signed up for that yet.
Go back over there.
You signed up?
Is that on dashboard? No.
What?
Is the waypoint thing on the dashboard? The whole little dashboard?
No. It's just a thingamajig. Some of the posters I have posted around that you scan the. Excellent.
What weekend is that?
It is May 10th. Dan, signing up for Waypoint for May 10th?
Probably not.
Why?
Well, hopefully have my AVPs coming week, so.
That's a fair reason. I won't even call it any excuse. Fair reason. Brian.
That's Saturday.
Yeah. And Anthony. Waypoints?
I've gotten there correct.
What? Oh, come on.
That's an excuse right there.
That's an
That is
excuse.
You got a freaking Yeti shirt. You're supposed to find that out when you get married.
I kind of, I don't know. For hearsay, I think he's doing the right thing. I don't know.
I'm just gonna do it so I don't have to work, I think.
Sorry. I like it.
You have a Barbie shirt over the street, did you wear it? I know the shirt.
Sam, you need to steal all his shirts and give him one.
Can you give me a Barbie shirt?
I feel like you'd rock it though. Like you make it.
Well, you're pretty close to being good right
Aw.
What is every dishes in my hand? They're all taking long.
Jealous, David.
I know.
That's right.
Exactly.
Yeah.
Except me.
Jeff, you share my pain.
Oh, wish I had that long hair. I am growing it, but that's also just because I don't want to get a haircut. Who else is going to be here for it?
I don't know yet. Well, you mean MAF wise or
Go ahead.
student wise? So in the lunchroom, on the window thing is
Oh,
people.
there's-
Yeah.
Do I need to sign on that too?
Yeah. Then I know and I can coordinate.
So that you
Like that?
is
Yeah.
so you
Right. I mean, I always appreciate that. Yeah, we'll be good. Because all the labs should be finished. And I'll just yeah.
Somebody's good.
Yeah.
Okay, whole plan.
Sounds
If something changes, like 5 or something, say, hey, Kirk, I'm making you block it.
oh, no, thanks. compressor on our engine. So here we have a lovely diagram, and let's start up here. What is this area called? Inlet. Nailed it. Sydney, you got a gold star house. And then what is this area in? Wait, actually, what's this big old, great big blade is up here? Fan. So we've got turbo fan going on. And then what are these through here? Compressor section. What's this combustion? And what's in here? Very good. So anytime you come to a diagram, just orient yourself. What's our big main components? So what is really, this is probably cool, is what's coming off of here. What is this area here? Excellent. Fan bypass. So we get our cooling air, and we're going to duct that into areas that we need that cool air. So look at this. It comes in here and here for our, what overall section is this? Very good, as compared to cool section. So we're taking cool air and ducting it around for our hot exhaust area. And what could we be using it for in here? And also turbine blades, so if they're those that receive cool air. And then here, I was going to ask you, but it's written up here. All of these red areas, we're going to talk tomorrow about bearings, and more specifically why they're there, types of bearings, how they're cooled. But some of them are going to have labyrinth seals, which need air, and so we're going to take some of this air and use them for our bearings and seals. Here on our compressor, we're taking 5th stage and 8th stage and using that for airframe systems. And then we have 2 and 4, HP2 and 4 coming in off of here, and using that going into possibly our bearings on here, and coming back here, going down through there. Kurt, did you have anything to add
No, you're doing a great job.
to this one?
What's the little one for the coolant?
Which little one?
The one, so go to, straight up, right there.
So this one, you're correct, it's cooling coming from our fan bypass. And that's a good question, whether it's coming in here to help keep this area cool. That's not real specific exactly what component it's going to. Yeah.
Along the bottom, too.
Right. Most of these are similar on the top and bottom because you have it going the whole way around our engine.
So instead of problem, if I look at that slide, I just see the prehistoric beetle. That's what it looks like.
That's great. Oh, that looks, I just saw it. Like So it is fan air
So there's a little bit of pressure through it.
ducting back, and this is going into whatever ducts and chambers are going, like they're out on the table.
Like the hollow
Yes.
goes through there. So in your compressor section, after it goes through your combustor, you just got
Wait, what?
fairly high
Say again.
pressure. The air coming out of the combustor going to the turbine.
To the turbine, yeah.
Fairly high pressure compared to the outside air. So what
Ah.
keeps the air from coming out of those holes and not going back in those?
Yes, so it's all separate. So this isn't real good to show, but our combustion air is going over the turbine blades. What can I use to show? So it's just coming off combustor, hitting turbine blades. Where in our hub possibly or other areas are all the ports where the cooling air is being ducted internally into,
Right.
up to the root.
And it's got holes in there to let the cooling air come out of it. So is it just
Okay.
some triple force that keeps the air coming out and that doesn't let the high pressure come back in?
I see what, yeah. Well, I'll attempt and I'll let Kirk take it. So it depends where that's coming from. Where is your highest pressure
Diffuser.
in a diffuser? And I can't tell with this diagram, but if they're taking it off of the diffuser,
Mid-level across.
it'll be higher pressure coming out. But also, the direction of the air going through the turbine section is all directed by the blades. They're extracting it, and then the stators are increasing it onto the next section, so it's heading that way rather than trying to dive into the ends of the blades. You have
Yeah. Just the way the holes are drilled in the turbine blades, there's no holes on the turbine blades that would act like ram air from the combustion to overpower the cooling air. So the holes are actually drilled on the turbine blades so that it can come out and flow with the combustion air. Join the combustion air. That's the fight.
Did I answer your question? Good thinking. Any other questions on? So that's kind of internally for the engine. And then, of course, we're going to steal bleed air and use it for other things. So here is our one of our main engines, and then we go down here. The other one is cut off. But here is our APU. So to start this engine, we can use APU air to there, to our air turbine starter, or we can use, if we have one engine, this other engine started, we can use air from there to start this engine, or we have the external air connection from a ground power unit to start that engine. Then we have, let's see if I can do this in somewhat orderly fashion. So we'll start with this engine here. Here is fan air port, so we can take air from the fan air, and if any of this air, bleed air, we're taking from the compressor is too hot, wherever it's going, our fan air is cool, so we steal that to cool down this compressor bleed air, depending where it's going, what we need it for. And out here we have, what do you think, Cal AI, artificial intelligence? I heard, maybe, you had this class, well, the airplane class. Air inlet? Any other ideas? What would we need hot bleed air for on our towels? our warm bleeder isn't hot enough for our anti-icing needs, we can go back here to our stage 8, where we're even warmer, and duct that air up to our anti-ice to get that nice and hot. And of course we got bleed ports and pressure regulators. Oh, here we have, what do you think? This is a CPAP. Oh, I think I heard it. For so air conditioning. So air conditioning for our cabin. And then an isolation valve if we need to isolate our sides. Let's see, what else do we have here? Kurt, we have, so yeah, controls for all our systems. APU, electronic control unit, go into there. And
this is aircraft specific. This is the feeder system actually up below. So whatever aircraft you learn, whether it's a P-6, like a P or something like that, it's not going to be different. But this is just one example of how feeder is used.
it's all, yeah, different valves, different options, ways it can be directed. And this is just zoomed in of, yeah, taking our fan air options for our anti-ice, warm, extra warm, and the air turbine starter that has 3 options.
That bleed pressure regulator valve, that's on the left column there. That's what, when it starts feeding your aircraft, that's going to be one of the main things that'll just make sure it maintains about 45 psi in the whole aircraft system.
Question. Yes.
On the slide back, what is the external air connection for?
This is for our ground power unit if you're not going to use your APU for your air turbine starter or the other engine, then you can have a ground power. Yeah. These, I believe, are electrical connections, just for all our controls. Any other questions? If there are no other questions or comments, I will explain what's expected for lab today. And while you are on break, I was sneaky, opened up another lab. So, the lab I opened is on APU. How about that? And actually, let me see if I can go back here and double check. I believe there is only one more lab I will be opening probably tomorrow. So, you can breathe a sigh of relief for that. Use your time wisely this week to make sure you're getting all your Moodle labs done in the midst of your practical labs. For this one, it tells you answer the following questions using your textbook. I forgot to edit that, so it is version B, Bravo, rather than Alpha. Jefferson Power Plant textbook, which I had told you in that turbine engine section, it does have a part on APUs, so that will be helpful. And then the Gulfstream 550 maintenance manual, and the Sikorsky 92 maintenance manual. And I just want to point that out to you. The Sikorsky is going to be be group 6, 7, and 12 do analysis. And groups 10, 11, 12, and 13 doing fuel nozzles, which you're gonna have time to get through those, but Stephen and Sydney, you get to go first. After you guys go, then grab, we'll just do it this way. David and Nate come up to the top. Grab John and Austin. John, grab Sam and Ryan. Okay. And then